Good morning. I am Dr. R. Murli, Professor, Department of Mathematics, Dr. Ambedkar Institute of Technology, Bangalore. I am delivering lectures in Engineering Mathematics 2 with subject code 15MAT21. The topic of my lectures is partial differential equations, which comes under module 3. Now, in the previous sessions, we have learnt the following. What is a partial differential equation? In short, written as PDE. How to form a PDE? By the elimination of arbitrary constants in a given relation. How to form a PDE? By the elimination of arbitrary functions in a given relation. We have seen examples related to the removal of 1 and 2 functions. In the previous session, we have formed PDEs by eliminating one arbitrary function from a given relation when the relation is in the form u equal to f of v and f of u comma v equal to 0. So, in both cases you remove the function f to form the PDE, and we have seen that such PDEs in which you remove one function will be PDEs of order 1. Now, since we study PDEs, now in today's session we go further and discuss the solution of non-homogeneous PDEs by a direct integration procedure, which is solution of non-homogeneous partial differential equations by direct integration method. Now, we have to recall again the following standard notations. So, throughout our lecture today, we will consider z as function of two independent variables x and y. That is, z is considered to be z of x comma y. This is the standard notation. In some cases, the independent variable may vary. For example, x and y can be replaced by say x and t. That depends on the problem. And also the dependent variable need not be necessarily z, it can be u or v or f, anything that is given in the problem. But as a standard terminology, we assume z as a function of x and y. Also, we have the following notations: dou z by dou x is p, dou z by dou y is q, which are the first order partial derivatives. Dou square z by dou x square is r, dou square z by dou x dou y or dou square z by dou y dou x, both of which, my friends, which you know are one and the same, is s, and finally the second order partial derivative with respect to y, which is t. In the previous sessions, we have understood that a PDE containing p and q will be a PDE of order 1, whereas any PDE that involves one or more of the partial derivatives r, s and t becomes a second order PDE. Now, in today's session, we will be solving non-homogeneous PDEs by the method of direct integration. So, before we go into the actual problems, let us first see what is meant by a non-homogeneous PDE. As you can see, friends, if each term in the given PDE contains either the dependent variable, for example, in our notation we take z as the dependent variable, so it contains z, or one of its partial derivatives only, so it should have z and the partial derivatives of z like p, q, r, s and t and so on, then such PDEs are called homogeneous PDEs. Now, homogeneous PDEs will be our topic of discussion in our future sessions. Now, anything that does not satisfy any PDE that does not satisfy the above conditions becomes non-homogeneous. Then obviously, when you are given a problem, friends, the aim is to solve the problem, correct. It may be a quadratic equation, it may be a cubic equation, it may be some equation in x and so on. So, as far you have also studied differential equations, where you have obtained the solution of ordinary linear differential equations as the sum of the complementary function and the particular integral. Similarly, in a PDE, a solution which is also called an integral of a PDE is a relation between the dependent and independent variables. It is not some arbitrary relation. The important condition is that this relation should satisfy the given PDE. Such expressions are called solutions of the PDE. Now, in today's session, in this section, we consider non-homogeneous PDEs. My friends, remember, non-homogeneity is what was defined earlier and obtained by their solution by the direct integration method. Now, what is the direct integration procedure? Now, if the independent variables in the PDE are x and y, then during the integration procedure, the following points should be noted. That is to say, when we integrate with respect to x, because you will have more than one independent variable, we must add a function of y as an arbitrary constant, like f of y, g of y, h of y and so on. Do not repeat the functions, write every time a new function. Either you write f y, g y, h y, or you write f1y, f2y, f3y and so on. Similarly, when you integrate with respect to y, we must add a function of x as the arbitrary constant, like f of x, g of x, h of x, or f1 of x, f2 of x, f3 of x, etc. Now, how do you actually use this? Let me illustrate one simple example. Suppose I have this non-homogeneous PDE, dou square z by dou x dou y equal to 3x plus 2y. Now, by notation, this is z x y equal to 3x plus 2y. So, what is the aim here? It is to solve this equation. More importantly, it is to obtain the value of z that will satisfy the given PDE. So, how to go about that? So, whenever you are given in notation form, follow this arrow. That is to say, from z of x y, you first integrate with respect to x. Okay? Integrate with respect to x, that will give you z y. Then z x y with respect to x will give you z y. Finally, integrate with respect to y to get the solution z. So, in this example, I will first integrate with respect to x, treating y constant, because x and y are independent variables. When you integrate with respect to one independent variable, the other independent variable will be a constant. So, when you integrate with respect to x, the left hand side z x y changes to z y equal to integration of 3x with respect to x is 3x square by 2. As far as 2 into y is concerned, both are constants. So, it will be 2y into integration of the remaining 1, which is equal to x. You must integrate all the terms. Wherever you come across a constant term, remove the constant term outside and integrate the remaining 1 there, which is x. So, in this case, 2 and y are both constants. If these values, these two terms are taken out, you are left with 1, whose integration with respect to x is the variable x itself. Then plus, because you have obtained or you have done an integration with respect to x, add an arbitrary function of y as the constant. Next, from z y, we now obtained the solution z, which is by integration with respect to the variable y. So, when you keeping x as the constant term. So, In the first term, with respect to y, 3x square by 2 is a constant. So, you are left with the constant 1. So, if you take 3x square by 2 outside, the remaining 1 will give you an integration with respect to y as y itself. Then the second term here, there is a y term which is 2 into y, and integration of y is y square by 2. So, I get 2 y square by 2 into x plus, even though f of y is an arbitrary function of y, f of y means that it contains y terms, and because you are integrating with respect to y, you cannot leave this is not a constant. So, because f y is arbitrary, you can integrate f y with respect to y as integral f of y dy. Because you have integrated with respect to y, add a function of x as the constant, say g of x. Do not repeat the functions, you must try to understand this notation, because you are integrating f y assumed earlier again with respect to y, which will give you integral f y dy plus the constant of integration, which is g of x. So, this becomes the solution of the given PDE. Now, as we proceed in this lecture, we will be looking into more examples of such non-homogeneous PDEs. Now, what was now illustrated on the board here is specified here. In some cases, the arbitrary functions in the solution of the PDE, for example, f of y and g of x, can be obtained by using the given set of conditions which will be specified along with the PDE. So, if a set of conditions are specified with the PDE, you will be able to determine the values of the functions that arise during your integration procedure. This solution is also called a particular solution of the PDE. Second, during the integration process, the following method can be applied as was illustrated here. For example, if the partial derivative given to you is zxy, then to obtain z as the solution, we first integrate with respect to x, keeping y constant as was illustrated here. So, from z of xy, you first integrate with respect to x to get zy, and then integrate with respect to y to get the solution z. Similarly, if you have zxx, which is dou square z by dou x square, we first integrate with respect to x, keeping y constant, and then again integrate with respect to x to obtain the required solution, which is the value z. Now, to exactly illustrate our concepts, let us solve the following examples. The first example, solve dou square z by dou x square equal to x minus 3y. So, notice that this is non-homogeneous because it not only contains the dependent variable and its partial derivative, but also the dependent variables in the equation. Clearly, the definition says homogeneity will mean only the dependent variable and its partial derivatives, no other terms, whereas this equation contains the dependent variable, its partial derivative, as well as the independent variables x and y. So, if I use notation, you know that dou square z by dou x square, which is r, is z x x. So, how to integrate? Follow this direction. First, integrate with respect to x, which will remove the first subscript x. During this integration, treat y constant. Next, after the first integration, it leaves you zx, which is dou z by dou x. Then integrate again with respect to x, keeping y constant to obtain z, which will be the required solution. So, the given PDE is zxx equal to x minus 3y. So, first we remove the first x in the subscript, integrating with respect to x, treating y as constant. As I told you friends, observe zxx is now changed to zx. So, left hand side will be zx. Integrate x, integration of x is x square by 2. Then what is the integration of 3y? Because y is a constant, 3 and y are both constants. So, when you keep 3 and y apart, you are left with 1, and integration of 1 with respect to x will give you this variable x. So, it is minus 3xy, and because the integration is with respect to x, add a function of y as the constant. Next, from zx, you have to find z, which will be the required solution. How to get z from zx? So, integrate again with respect to x. Remember friends that when you do this integration, y will be a constant again. So, go to the zx above, go to this zx, okay, and integrate this expression with respect to x. So, what is zx with respect to x? First, zx on integration will give zx on integration should give you the value z. Next, the integration of x square by 2 will give you x cube by 3, sorry, x cube by 3 into 2, which is x cube by 6, that there here. So, from zx you get z, x square by 2, x square, integration of x square is x cube by 3 into the 2 in the denominator will give you x cube by 6, minus 3 into, you have x term here, other terms are constants. So, x is x square by 2 into y. So, you get minus 3 x square by 2 into y. It is interesting to note that here this is a function of y. So, when you integrate a function of y with respect to x, function of y becomes a constant term. So, keep it aside, you are left with 1 which whose integration with respect to x is x. That is why you have this x in the integration, and because you are integrating with respect to x, you finally add a function of y, say gy, as the constant. So, that z equal to x cube by 6 minus 3 x square by 2 y plus x into f of y plus gy becomes the required solution. Let us go to the next example. Solve the non-homogeneous PDE dou square z by dou x dou y equal to sin 2x minus 3y plus 18 into x square into y. Now, observe that this is a mixed derivative, in the sense by notation it is zxy. So, how do you obtain the solution? As was illustrated in the previous examples, you first integrate with respect to x by treating y as constant. So, that will give you the derivative zy or dou z by dou y. Finally, integrate with respect to y to give you the solution which is equal to z. So, let us go about this. First, we apply notation in the LHS, zxy equal to sin 2x minus 3y plus 18 x square into y. So, integrating with respect to x, treating y as constant, the left hand side zxy changes to zy equal to integrate sin 2x minus 3y. What is the integration of sin 2x minus 3y? You have sin 2x minus 3y. So, when you integrate sin 2x minus 3y, sin is minus cos 2x minus 3y divided by the coefficient of x, which is equal to 2. Okay. So, sin 2x minus 3y on integration will give minus cos 2x minus 3y by 2, then plus the integration of 18 x square y will give 18 x square y with respect to x will give 18 x cube by 3 into y, which is 6 x cube into y. So, when you come back here, you have the integration with respect to y, zy as with respect to x, sorry, as minus cos 2x minus 3y by 2 plus 18 x cube by 3 into y plus, because you have done an integration with respect to x, you add the function f of y as the constant, or on simplification zy is minus cos 2x minus 3y by 2 plus 6x cube y plus function of y. Now, what is the aim? You have to get z. So, from zy you now get z by integrating with respect to y. So, when you integrate with respect to y, x becomes the constant. Now, integrate the expression here. So, zy changes to z, integration of minus cos 2x minus 3y by 2 with respect to y will be what? You know that integration of cos is sine. So, you get minus sine 2x minus 3y by 2, that is the integration of cos, into, you should divide by the coefficient of y, which is minus 3. So, the integration will read as minus sine 2x minus 3y by 2 into minus 3, or when you cancel the negative sign, it is sine 2x minus 3y by 6. Okay. Then the second term, integration of 6x cube into y here with respect to y is 6x cube y square by 2, and as was illustrated in the first example, since f of y is a function of y, its integration with respect to y will give integral f of y dy. You can leave it as it is, plus finally the constant with constant of x, which is the function g of x. So, that z equal to sine 2x minus 3y by 6 plus this is 2 3 times. So, 3x cube y square plus integral f of y dy plus g of x is the required solution of the PDE. As we discussed, friends, when you are given a non-homogeneous PDE without conditions, you just integrate and leave it as it is. But if conditions are specified along with the problem, these conditions are applied in the problem to also obtain the arbitrary, the constants that are assumed in the solution. Okay, that is illustrated in the next example. Solve dou square z by dou x dou y equal to sin x into sin y subject to the conditions dou z by dou y equal to minus 2 sin y when x equal to 0. So, how to apply this condition? Go to dou z by dou y, which you obtain in the sequence of integrations. In that, replace dou z by dou y by minus 2 sin y as and when x is 0, and z equal to 0 when y is an odd multiple of pi by 2. So, before applying the conditions given, let us first solve the given PDE. So, what are you given? Using notations, you know that dou square z by dou x dou y is zxy. So, given zxy equal to sin x into sin y. So, how do you get z from this? First integrate with respect to x to give you zy by treating y constant, then integrate with respect to y to obtain z by treating x constant. So, we will do that here. So, first take zxy sin x into sin y and integrate with respect to x treating y as constant. So, the left hand side zxy is transformed to just zy. In the RHS, integration of sin x sin y will involve only sin x, because you are integrating with respect to x, and it is known that the integration of sin x is minus cos x. So, you get minus cos x into sin y plus, because you are integrating with respect to x, you assume a constant of y as the function of y as the constant. So, you write f of y. Let us call that equation 1. To obtain the solution now, integrate with respect to y. So, zy is transformed to z, integration of minus cos x into sin y with respect to y, only sin y is the variable now with respect to y, and integration of sin y, my friends, is known to be minus cos y. So, you get minus cos x into minus cos y, which is cos x into cos y, plus f of y is a function of y. So, when you integrate with respect to y, it is changed to integral f of y dy, and finally, the constant of integration, which should be a function of x denoted by g of x. Let us call that equation 2. Now, we will apply the given conditions to the solutions obtained. You can observe, we now apply the given conditions to determine the functions f of y and g of x. When you do that, the solution will be a particular solution of the PDE. So, how to apply these conditions? Let us recall the following. During the first integration, you obtained this expression zy equal to minus cos x sin y plus f of y. Apply the first condition, given that dou z by dou y equal to minus 2 sin y when x is equal to 0. That is, zy equal to minus 2 sin y when x equal to 0. Now, how to apply this condition? Go to this solution, which is zy. What the condition means is, as and when you put x equal to 0 in the RHS, in the LHS, zy can be changed to minus 2 sin y. So, what happens to equation 1? That is this equation. Left hand side, you observe that my zy is changed to minus 2 sin y. In the RHS, when you put x equal to 0, cos 0 here is 1. So, it is minus sin y, 1 into minus sin y, you get minus sin y plus f of y. Now, this equation will help you to get f of y. What is f of y? Shift this sin y to LHS, you get minus 2 sin y, that if it goes to LHS becomes plus sin y. So, that it is minus 2 sin y plus sin y, which is minus sin of y. Now, you have obtained one of the functions f of y. How to obtain the second condition? Sorry, how to obtain the second function? Use the second condition given. Before you use that, update your solution now by substituting this function f of y in this solution. Substituting in 2, which is, I will show you the previous slide. When you finish the integration with respect to the second variable, you obtained this solution, correct? You obtained z equal to cos x cos y plus integral f of y plus g of x. Notice, friends, that f of y is already obtained now. So, that f of y can be substituted in the solution obtained, that is seen in the next slide. Equation 2 is written here. Because f of y is minus sin y, we will apply or substitute f of y here. So, when you substitute that, you get z equal to cos x cos y plus integral f of y dy becomes integral minus sin y dy plus g of x, and it is known that integration of sin y with respect to y is minus cos y. So, that you end with z equal to cos x cos y plus cos y plus g of x. For convenience, we will call that equation 3. So, what is the sequence? First, you obtain the solution. First, apply the derivative condition, which was zy, to obtain one of the functions. Substitute that function in the final solution and rewrite. Now, apply the other condition given. It is given that z is 0 when y is an odd multiple of pi by 2, or equivalently when y is 2n plus 1 into pi by 2. This condition is substituted in the solution obtained in equation 3. So, apply that condition. So, what happens when y is an odd multiple of pi by 2, y is 2n plus 1 into pi by 2. So, substitute here and z is equal to 0 from this condition. So, when y is this, z is 0. So, LHS z will be 0, wherever you find y here, cos y will be replaced by cos 2n plus 1 pi by 2. The same thing happens here also, plus g of x. Okay friends, that is written here, but it is known that cos 2n plus 1 pi by 2 is 0, cos of odd pi by 2 is 0. So, that gives, since these two terms are zeros, you are left with only gx becoming equal to 0. Now, substitute this back in your solution in 3, which is here in this solution, because gx is 0, we end up with the solution as z equal to cos x cos y plus cos y. So, what you should notice here friends is that in the final solution you do not find any of the arbitrary functions that were assumed in the solution. Both these functions have been determined using the given conditions. So, that finally you get a particular solution to the PDE in the form z equal to, take cos y common in these two terms, cos y into cos x plus 1. Let us move on to the next example, which will illustrate a similar type of solution. Solve dou square z by dou x square equal to x into y subject to the conditions z 0 comma y equal to 0 and dou z by dou y 1 comma y equal to log 1 plus y. So, before solving the problem, let us analyze these conditions. So, in this example, the dependent variable is z and the independent variables are x and y. So, z should be obviously z of x comma y. Even though in the final solution we do not write this, we do not write z of x comma y, it is understood that as and when you find the solution as z, it is nothing but z of x comma y itself. So, what does this condition mean? Try to relate with this. What is z of 0 comma y equal to 0? Observe that when you compare these two, x is 0, correct? So, this condition means that when x is 0, z is 0. Okay, this condition to be applied later in the solution. Similarly, what is dou z by dou x 1 comma y equal to log 1 plus y? Compare this with this. You can see that x is 1, no change in y, correct? So, this condition is interpreted as when x equal to 1, dou z by dou x is equal to log 1 plus y. So, let us solve the PDE using notation. The given PDE is zxx equal to x into y. As you know friends, zxx will first become zx by integrating with respect to x keeping y constant, and again that zx will become z by integrating again with respect to x treating y as constant. So, let us perform the first integration. So, zxx with respect to x in the LHS gives you zx, x into y with respect to x is x square by 2 into y because y is constant, plus the constant of integration which is a function of y. We move on to the second integration with respect to x keeping y constant. So, that should give you integration of x square by 2 y in x square by 2 y, y is a constant, integration of x square is x cube by 3. So, x cube by 3 into 2 in the denominator will give you x cube by 6 into y. Then let me repeat here again, f of y is a function of y. So, when you integrate with respect to x, it is a constant. So, you keep it aside, you are left with 1 whose integration with respect to x is x. So, you get x into f of y plus finally the constant of integration which is a function of y, say g of y. We will recall these two expressions again in the solution. when we try to apply the given conditions. Always remember, apply the derivative condition first. So, by data, dou z by dou x 1 comma y is log 1 plus y. As we discussed earlier, this condition means that dou z by dou x or zx is log 1 plus y whenever x is equal to 1. So, we recall our solution obtained in equation 1 which is this. Hence, equation 1 which is zx equal to x square y by 2 plus f of y becomes, apply this condition. When you put x equal to 1, replace zx by log 1 plus y. So, what happens in the LHS? Log 1 plus y will be, when x is 1 here, you get 1 by 2 into y by 2 plus f of y. That gives you immediately f of y as, shift this y by 2 to LHS, log 1 plus y minus y by 2. Now, to obtain the second condition, before you apply the second condition, substitute this f of y equal to log 1 plus y minus y by 2 in the solution obtained in equation 2 here. Okay? It is substituted here, that you can see written here. Equation 2 is this. In equation 2, the fy here is replaced by the fy obtained here. So, you get z equal to x cube by 6y plus x into fy is log 1 plus y minus y by 2 plus g of y. Now, apply the second condition which is z 0 comma y equal to 0, which means z is 0 when x is 0. So, for this we will recall our equation 3 again, which is this equation obtained by substituting f of y. So, that is written here. In this, apply this condition. When x is 0, z is 0. So, left hand side z will be 0. Wherever you find x, x value is 0. So, this is 0, this is 0, then you have 0 here, leaving you just g of y equal to 0. Finally, substitute this g of y here to obtain the particular solution to the given example, which is z equal to x cube by 6y plus x into log 1 plus y minus y by 2. Let us move on to the next example. You should notice a slight variation in this problem that we will explain as we go about solving the problem. So, solve dou square z by dou x dou y equal to x by y, subject to the conditions dou z by dou x equal to log to base e x, log to base e x and log x are one and the same when y equal to 1, and z equal to 0 when x equal to 1. First, using notations, the given problem can be written as z x y equal to x by y. But there is a problem here in the following sense. If I keep z of x y as it is, okay, I will first integrate with respect to x, which will give me z x, and then with z y, I am sorry, and then I integrate with respect to y to give me z. But can you identify the problem here, friends? Observe that when I do x y with respect to x, I get z y, correct, and then z, but this condition given does not match this partial derivative. That means to say, you cannot apply the derivative condition dou z by dou x to the partial derivative dou z by dou y. So, that is written here, z x y on integration with respect to x keeping y as constant will give z y. Later, integration with respect to y will give the solution z. But notice that the first integration with respect to x, which gives z y, is not compatible with the initial condition dou z by dou x equal to log x when y equal to 1. Hence, to overcome this, just use the fact that z x y is the same as z y x. This is very important, friends. Without this, the given conditions cannot be applied to the given problem. So, what we do? So, from equation 1, what was given was z x y equal to x by y is written as z y x equal to x by y, and you know that z y x first integration is with respect to y keeping x constant. We will do that. integrating with respect to y, treating x constant, we get in x by y, x is constant, integration of 1 by y with respect to y is log y. So, zx will be x log y plus the constant of integration which is a function of x. We will call that equation 2. Next, to obtain the solution, we integrate equation 2 above with respect to x treating y constant. So, in x log y, x is the variable. So, integration of x is x square by 2 into log y plus this being a function of x should be integrated with respect to x, which will leave you integral f of x dx plus, because the integration is with respect to y, you have the constant g of y. Now, applying the condition dou z by dou x equal to log x when y equal to 1 on equation 2, apply here, you get when y is 1, zx is log x. So, replace zx by log x, that you see here, LHS is log x. In the RHS put y equal to 1. So, you get x log 1 plus f of x, but log 1 being 0, this cancels, leaving you f x equal to log x. Before proceeding to apply the next condition, substitute it here, sorry, not here, here. So, you have in equation 3 on substitution of f x, z equal to x square by 2 log y plus integral f of x will become integral log x dx plus g of y, that you can see illustrated here, but integral of log x is like x log x by x, sorry, x log x minus x, sorry, that is a standard integral, call that equation 4. Now, apply the other condition given to you, given that z is 0 when x is 1. So, what happens to 4? Z will be 0 when x is 1, this is 1 by 2 log y, this is 1 into log 1 minus 1 plus g of y, but log 1 being 0, this term cancels. So, you are left with 0 equal to 1 by 2 log y, this minus 1 plus g y, or that gives you g of y as, shift these two terms to LHS, 1 minus half into log y. Substitute finally this g y in equation 4 for the required solution. Let me remind you friends, again it is a particular solution. So, finally, you have z equal to x square by 2 log y plus x log x minus x plus g y is replaced by 1 minus half log y. You can do a simple arrangement here. Observe that the first and last terms have common factor half. So, take half out, you get x square minus 1 into log y plus x log x minus x plus 1, which is the required solution. Now, in the next example, we will show a solution where the independent variables are x and t and not x and y. So, in this case, solve dou square z by dou x dou t subject to the conditions z x comma 0 equal to 0 and dou z by dou t 0 comma t equal to 0. Also show that z goes to sin x as t goes to infinity. So, observe that in this example the independent variables are x and t, whereas the dependent variable is still z. So, instead of z equal to z x comma y, it is z x comma t. So, what does this condition mean with reference to this? What does this condition mean with reference to this? First, let us analyze this. Z x comma 0 equal to 0 when compared to this will give you t equal to 0. So, it means when t is 0, z is 0. What is the implication of this condition? X and t is 0 comma t. So, this means when x is 0, dou z by dou t is equal to 0. So, let us go about the integration by notation. Z x t is e power minus t cos x. First, we integrate with respect to x, treating t constant. So, z x t, you remove x to get z t. So, when you integrate with respect to x, integration of cos x is sin x. So, you get z t equal to e power minus t sin x plus, remember, because the variables are x and t, the constant should be function of t, not function of y. So, it is f of t. Integrating again now with respect to t, keeping x constant, integration of e power minus t is known as minus e power minus t into sin x. This is a function of t, integrating that with respect to t, you get integral f of t dt plus constant now becomes a function of x, which is g of x. Now, apply the given conditions, but dou z by dou t 0 comma t equal to 0, which means dou z by dou t equal to 0 when x is equal to 0. Using this condition, equation 1, which was earlier this, becomes, so replace dou z by dou t or zt by 0 when t is 0. So, what happens? Left hand side will be 0 when t is 0, sorry, when x is 0, I am sorry, dou z by dou t equal to 0 when x is equal to 0. So, dou z by dou t is in the LHS is replaced by 0, when x is 0, sin 0 is 0. So, first term is 0 plus f of t, which gives you f of t equal to 0. Now, before applying the next condition, substitute this f of t equal to 0 in equation 2 here. So, z becomes minus e power minus t sin x plus f of t becoming 0, this is 0 plus g of x. Now, apply condition 2, z x of 0 equal to 0, which means z is 0 when t is 0. Apply that here. Z is 0 in the LHS, when t is 0, e power 0 is 1. So, you get minus sin x plus gx, or gx is equal to sin x, which you can now substitute back in equation 3, giving you the particular solution as z equal to minus e power minus t into sin x plus sin x, which is a particular solution. Now, finally, as t goes to infinity, it is known that e power minus t goes to 0. So, the first term becomes 0 in the solution. So, z immediately becomes sin x. So, that you say that z goes to sin x. The next example we illustrate is a partial derivative of order 3. So, solve dou cube z by dou x square dou y equal to cos of 3x plus 2y. So, by notation, this is z x x y, 2 x's here, dou x square. Suppose you have dou x dou y square, it is z x y y. Okay. Dou cube z by dou x cube is z x x x. Similarly, dou x square dou y is 2x and 1y. So, how to do this integration? First x keeping y constant, then x keeping y constant, and finally y to get z. So, first we integrate with respect to x keeping y constant. So, x x y becomes x y, integration of cos 3x plus 2y is sin 3x plus 2y, with respect to x will mean you divide by the coefficient of x, which is 3 plus a function of y. Then once you come to z x y, it is the usual method. Z x y is then integrated with respect to x, which gives you z y. Integration of sin is minus cos 3x plus 2y. Again, you are integrating with respect to x, coefficient of x is 3. So, the 3 into 3 becomes 9. F of y is a constant with respect to x. So, keep it aside and integrate the remaining one, which will give you x f y, and finally g y, which is the constant of integration. Finally, integrate with respect to y to give you z equal to, when you integrate with respect to y, notice that the coefficient of y is 2. So, minus cos 3x plus 2y is transformed to minus sin 3x plus 2y by 2. Already you have 9 in the denominator, so that gives you 18, 9 into 2 18, plus in x into f of y, integration with respect to y, x is a constant. So, that you see written here outside, into integral f of y dy, plus you cannot ignore g of y because that is a function of y and you are integrating with respect to y. So, that gives you integral g of y, finally ending with a constant of integration h of x. So, friends, in today's session we have seen what is a non-homogeneous PDE and how to solve such PDEs by a direct integration procedure. Now, I end this lecture with a few practice problems which is shown to you. Thank you, friends.